Imagine this. The crowd is going wild as the star basketball player leaps into the air, ball in hand. He arcs his back and the ball leaves his fingertips, soaring in a perfect parabola towards the hoop. Swish, the buzzer sounds and the crowd erupts. That, my friends, is projectile motion in action. Projectile motion is the captivating dance of an object, a projectile as it traverses through the air under the influence of just one force: gravity. From a kicked football sailing across the field to a golf ball launched towards the green, projectile motion is everywhere in the world of sports. But projectile motion isn't just about sports. It's a fundamental concept in physics that governs the movement of countless objects around us. Think about the graceful arc of a fountain, the terrifying trajectory of a missile, or even the simple act of throwing a paper ball across the room. Each of these scenarios can be understood through the lens of projectile motion. In the upcoming sections, we'll embark on a journey to unravel the mysteries of projectile motion, breaking down this captivating phenomenon into bite-sized pieces that are easy to digest. We'll explore the basic concepts, delve into the equations that govern its motion, and discover how understanding projectile motion empowers us to analyze and predict the movement of objects in our world. Before we tackle the complexities of projectile motion, let's first lay a solid foundation by understanding motion in one dimension, or in simpler terms, motion in a straight line. Picture a car cruising down a straight highway. To fully describe its motion, we need to consider a few key concepts: displacement, velocity, and acceleration. Displacement refers to the change in position of an object. It's like saying the car traveled 100 kilometers eastward. Velocity, on the other hand, is the rate at which an object changes its position. It tells us not just how far the car traveled but also how fast, for example 100 kilometers per hour eastward. Finally, we have acceleration, which measures how quickly the car's velocity changes. Is the car speeding up, slowing down, or maintaining a steady speed? Acceleration provides us with that information. For instance, if the car increased its velocity from 0 to 100 kilometers per hour in 10 seconds, it experienced an acceleration. In the context of projectile motion, we'll be applying these concepts of displacement, velocity, and acceleration to both the horizontal and vertical components of an object's motion. Why? Because even though a projectile might follow a curved path, we can break down its motion into horizontal and vertical components, each behaving independently of the other. This remarkable characteristic of projectile motion makes it much simpler to analyze and predict. Now, let's return to our basketball player. When the player throws the ball, it embarks on a journey known as ground-to-ground projectile motion. This simply means the projectile's journey begins and ends at the same vertical position, the ground level. The path traced by the basketball isn't random. It follows a beautifully symmetrical curve called a parabola. This parabolic trajectory is a hallmark of ground-to-ground projectile motion, and it arises from the interplay between the object's initial velocity and the relentless pull of gravity. One of the most fascinating aspects of ground-to-ground projectile motion is that the horizontal and vertical components of the projectile's motion are independent of each other. This means we can analyze them separately, making our calculations simpler. The horizontal motion experiences no acceleration, assuming we neglect air resistance. The projectile continues moving at a constant horizontal velocity throughout its flight. The vertical motion, however, is dominated by the force of gravity. As the projectile ascends, gravity works against it, causing it to slow down until it momentarily comes to a halt at the peak of its trajectory. Then, as it descends, gravity pulls it downwards, causing it to accelerate.